What's up guys, it's me Sir Ernest, and today we're going to talk about the bisection method to find the root of a function. But first let's recall the basic idea regarding root finding method. If we have a function given by this, we can easily graph this function and estimate the roots of a function by just looking at the graph. So estimated roots of this function is around negative 0.5 and positive 2.5. So that's your estimated roots of this function. So that method is called the graphical method of finding the root, and that is a very quick way but inaccurate or imprecise way to determine the roots. Okay, so when we take the roots of this function, we want to take the exact root of this function. We equate this function to 0, and then we solve the quadratic equation or quadratic formula. Okay, as we notice that a more precise root of this function, which is from the quadratic formula, is 2.5811 and negative 0.5811, which is very close to our estimated root earlier. So as I mentioned earlier, this quadratic formula, by following this quadratic equation, is called the direct method. It is an analytical method or an exact method to determine the root of a function. But however, this quadratic formula is only applicable for quadratic equations. Of course, we can use some approximation methods, such as graphical method, a trial and error method, and some numerical methods. In this video, we're going to look into a type of a bracketing method called the bisection method. Okay, a variation of the bisection method is the false position method, wherein the difference between the two methods is just how we estimate the root given a bracket. We can also do some open methods, such as fixed point iteration, Newton-Raphson, or secant method, but that is beyond the scope of this video because we're only going to focus on the bisection method. Now let's look at the bisection method. So the bisection method employs several iterations, and then in each iteration we're going to estimate the root, and upon several iterations, that estimated root becomes very close to the exact root of the function. So imagine we have this equation or this function 2x squared minus 4x minus 3. So if we're going to plot this function from x equal to 0 to 5, so we're going to have this graph, this blue graph. So again, as you notice that the function has a root somewhere about 2 point something, 2.5. Okay, so here I'm going to present to you some basic steps on determining the root of the method. Now, first step is choose an initial bracket and calculate the midpoint. So what do we mean by this? So for example, I'm going to choose these two values XL and XU, and this defines our bracket. XL pertains to the lower end of the bracket, and XU refers to the upper value of the bracket. Now when you calculate the midpoint, just like the name of the method suggests, we're going to bisect this bracket into to determine the midpoint. We call the midpoint XR, and XR is equal to XL plus XU divided by 2. So this marks your XR, and for this first iteration, we consider this as our first approximate root. It may or may not be close to your approximate root, to your exact root, but we will use this approximate root for the next iteration. Now, step 2. Let's evaluate the value of your function at these 3 points, XR, XL, and XU. So for xr, the value of your function is given by this value for xl and for xu. Now, next is to check if the root is in between xr and xu, or xl and xr. So how do we do this? So we're going to do some conditions. Okay, so this conditions is the one that is different from what was presented in your MATLAB module. So in our case, we're going to compare the product of the value of the function at xr and xu. So in this case, we're going to check we're going to multiply the value of fxr and fxu. Okay, so we're going to check if the product is less than 0. So what do we mean by this? So that means fxr and fxu have different signs. If one is negative, one should be positive. Okay, because for example, if we're going to check it here, fxu and fxr are both positive. So when we multiply them, it is positive. So if it is positive, so that means the root is not in this bracket. Okay, because if it is in this bracket, fxr and fxu will have different signs, just like in the second condition. If fxr times fxl are different in sign, so that means their product is negative. So if that's the case here, as you can notice here, the root is found between xl and xr. So that means for the next iteration, we're going to use the new the xr computed in this iteration to be our new xu. Okay, and then we're going to have a smaller bracket for our next iteration. So we're going to the next iteration using the new bracket. Now, for the succeeding iterations, we're going to choose the new bracket found in the first iteration, and then we calculate the midpoint. Now, this new midpoint, xr, is our updated approximate roots. And then, as I mentioned before, we're going to evaluate the value of your function at these 3 points. And we're going to check if the root is in between xr and xu or xr and xl. Now, so you will notice that the product of xr and xu is less than 0. So we're going to use xr as our new iteration. Comparing that here, we can see that the product of xr and xl, fxr and fxl, though the two functions are negative, if you multiply them together, that means they are it is positive. So therefore, the root will not be found here. So this becomes our new root. The xr, the xr that we computed in this iteration will be the new xl for the next iteration. So the new bracket will be this bracket. Okay, and then we repeat the process until you reach your desired number of iterations. So one way to iterate is that you can set the number of iteration and hope that by the end of the iteration, we could arrive at a good approximate or good estimate of your root. However, what we can also do is we could set a stopping criterion. Okay, if we're going to use a stopping criterion, we will let the computer check whether your estimated root xr will be within or is within your allowable error. And if this stopping criterion has been met or is met, we are going to stop the iteration. Okay, so in this case, we are going to set our stopping criterion either explicitly, like setting it, for example, the error should be less than 0.1%, or we can use the the determining the EA using the formula presented by or proposed by Scarborough, just like what we discussed before. Okay, so in the next video we're going to implement this in MATLAB and see how our program will behave. Okay, so thank you very much for watching this lecture, and I hope to see you guys in the next. Bye bye.